Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack Series.
Hello, everyone. It's really wonderful to be back.
Today, we are exploring programmable matter.
Mm.
And I have to admit, ever since I started digging into the material for this, I've been looking at everything on my desk a little differently.
Oh.
Yeah, I mean, my coffee mug, this microphone, the walls, it all just seems so static,
Yeah.
so boringly permanent.
I think boring might be a little harsh. I mean, for thousands of years, those materials have been doing exactly what we wanted them to do.
Which is what? Just sit there.
Just sit there, stay put, don't break. A brick is a brick. Its job is to be reliable and, unchanging.
That's a fair point. You want your house to be made of something that doesn't just decide to become a liquid one morning.
Exactly. But what we're talking about today is this fundamental shift away from that idea. We're on the edge of moving past static objects.
We're talking about physical objects that can change their properties on command. Their shape, their density, maybe their color, their elasticity.
All of it. Think about it like software. Software changes pixels on a screen. We're talking about a similar level of control, but over the actual atoms in the physical world.
That's a huge leap. You're saying we're moving out of what you might call the Stone Age of materials.
That's a perfect way to put it. Not that we're using stone tools, but
Right.
our relationship with matter has been, for the most part, passive. If you need something hard, you find a hard material, like steel.
And if you need something soft, you get rubber or cotton. You pick the material for its inherent fixed property.
Precisely. You don't ask a steel beam to suddenly become flexible because you need it to bend around a corner. You have to get a different object.
Right.
But we're entering a new era, an era where the core idea is that information is physical.
Information is physical. I've heard that phrase. It sounds like a bumper sticker for a theoretical physicist.
It is. But it's also the guiding philosophy for this entire field. We are blurring the line between computer code and the physical world. It's not just about processing data anymore, it's about processing matter.
We're moving from hardware to, what would you call it? Shapeware.
Shapeware. I like that. It captures the essence of it perfectly.
So for everyone listening, here's how we're going to structure our exploration today. We'll start with the foundations. Where did this crazy idea even come from? What are the basic concepts we need to grasp?
What we think we know.
Exactly. Then we'll get into the active debate. Because, needless to say, making this stuff is not easy. And scientists are arguing about some massive challenges like power and control.
The big engineering hurdles.
From there, we'll look at the frontiers.
Yeah.
The really cutting-edge stuff happening in labs right now. Things like chemical robots and 4D printing.
The things that might just change everything.
And finally, we'll talk about the implications. What does it mean for our society, for our economy, for the planet, when you can download a new physical object instead of buying one?
It's going to be a fascinating journey, from the theoretical to the very real.
Let's get right into it. Foundations. What exactly are we talking about when we say programmable matter? Because to most people, myself included, it sounds a lot like magic.
It does feel like that, but the scientific definition is actually quite rigorous. If you look at the literature, especially from places like DARPA or the MIT Center for Bits and Atoms, it's defined as matter that can change its physical properties based on user input or autonomous sensing.
Physical properties.
Yep.
So you mean shape?
Shape is the obvious one, yes. But also, its moduli, its conductivity, its optical properties.
Okay, hold on. Moduli. What's that?
Moduli refers to a material's stiffness. Think of Young's modulus, which measures how much something stretches or compresses under force. So programmable matter could, in theory, toggle between being as floppy as a piece of cloth and as rigid as steel.
So it's not just shape-shifting, it's property shifting.
That's the key distinction. And to really get the philosophy behind it, we have to talk about a physicist named Rolf Landauer.
And his bumper sticker, information is physical.
That's the one. He famously established that information isn't just abstract math floating in some conceptual space.
Right, I remember this from computing.
Mm-hmm.
It means every operation, every bit of information has to have a physical representation, an electron moving, a magnetic domain flipping.
Exactly. It takes up space, it uses energy. Landauer's principle shows that every time you erase a bit of information on your computer, a tiny but non-zero amount of heat has to be released into the environment. There's a physical cost.
Okay, I'm with you.
Programmable matter takes that idea and just flips it on its head.
How so?
Instead of using a physical thing to process abstract information, we're using computation to rearrange the physical thing.
Whoa, So instead of the matter being the substrate for the computer, the matter is the computer.
In a very real sense, yes. The computation is embedded into the very structure of the material. And, historically, this idea has been around for a while. The term itself was coined back in 1991.
1991. Really? That feels so early. We were still figuring out dial-up modems.
We were, but two researchers, Toffoli and Margulis, used the term to describe something called cellular automata.
Oh, right, like Conway's Game of Life. The little pixels that follow simple rules and create complex patterns.
Precisely. Back then, it was all about simulation. Fine-grained computing elements arranged in a grid. But as nanotechnology and microfabrication got better and better, the term slowly migrated from the world of simulation into the world of physical reality.
And of course, science fiction was way ahead of the curve here. I saw a note about Will McCarthy's quantum wellstone.
Yes, wellstone is a touchstone for so many researchers in this field. It's this fictional material, kind of advanced semiconductor.
That could mimic any other material, right?
Exactly. In the novels, it worked by trapping electrons in specific engineered quantum states, creating what he called pseudo-atoms. So you could program it to have the density of lead, the clarity of glass, the hardness of diamonds.
Just by changing the software.
Just by changing the software. And while the physics in the book is, fictional, it planted a seed in the minds of real scientists. How close can we actually get to a universal material?
Okay, so that's the dream. How do we actually build it? What are the fundamental building blocks, the atoms of programmable matter? I'm assuming we're not just moving individual carbon atoms around with tiny tweezers.
No, not yet. That's still incredibly difficult and slow. Any little bit of heat thermal noise just jiggles them out of place. So instead, researchers have developed these equivalents. And there are two main approaches here: the macro and the nano.
Let's start with the macro. That sounds more manageable.
That brings us to a field called claytronics.
Claytronics. It sounds like a futuristic pottery class. I know this is the work coming out of Carnegie Mellon and Intel.
It is. And the basic unit in claytronics is called a catum, a claytronic atom.
A catum. Okay, what is it? Is it like a tiny Lego brick?
Yeah. That's a good first thought. But a Lego brick is passive. A catum is an active computational unit. Imagine a tiny computer, maybe the size of a grain of sand, maybe a bit larger, like a ball bearing.
So it's a little robot.
It's a little robot.
Right.
Each catum can move, it can stick to its neighbors, and it can communicate with its neighbors. It's a swarm.
A swarm of tiny computers that come together to form a solid object.
And the core idea behind it is something called the ensemble principle.
Which means what?
It means that any individual catum is deliberately simple. You might even say it's stupid.
So one catum on its own can't do much.
Not at all. It has a tiny processor, a little bit of memory, maybe some electromagnets. It has no idea what the final shape is supposed to be. But when you get a million of them, or a billion working together,
They can form a wrench or a teacup or a replica of a person.
that's the goal. The idea of synthetic reality. It's like a hologram, as you see in the movies, but one you can actually touch and interact with.
Because it's made of actual matter.
Exactly. If the catums are small enough and packed tightly enough, the surface of the object they form would feel perfectly smooth to your hand.
Okay, but the big question then is, how do they stick together? If I build a chair out of these things, I don't want it to collapse into a pile of sand when I sit on it.
A very important question. And they don't use mechanical things like little hooks or latches.
I know.
Because at that tiny scale, friction and surface forces become dominant. Tiny mechanical parts would jam or break almost instantly. So instead they use something much more elegant: electrostatic latching.
Electrostatic. You mean static electricity, like when you rub a balloon on your hair.
A very powerful, very precisely controlled version of that, yes. By creating positive and negative charges on the surfaces of the catums, they can generate a strong attractive force to hold them together.
And you can turn that on and off.
Instantly. Which means the material could flow like a liquid one moment as the catums roll over each other, and then freeze solid the next as they latch into place.
But wait, maintaining an electric charge requires energy, right?
Yeah, it does. And that's a huge vulnerability if the power were to cut out.
My chair turns back into a pile of sand and I'm on the floor.
Potentially, yes. Which is a big part of the active debate we'll get to later.
Yeah.
They're working on geometries that can lock in place mechanically, so energy is only needed to change the state, not to maintain it.
Okay, so that's the macro approach. Tiny robots forming objects. What about the nano approach? This feels like where the really mind-bending science happens.
It is. This is the world of programmable atom equivalents, or PAEs. This is work pioneered by people like Chad Merkin at Northwestern University.
And here we're not using tiny robots.
No. Here, the atom is an inorganic nanoparticle. Often they use gold just because it's stable and easy to work with.
Okay, but a gold nanoparticle is just a tiny fleck of gold. It doesn't have a computer inside. It doesn't do anything.
That's true. In nature, atoms bond based on their electrons. Valence shells, ionic bonds, covalent bonds. That's the rule book of chemistry.
Right.
With PAEs, scientists throw out that rule book. What they do is they take these gold nanoparticles and they coat them with custom-designed strands of DNA.
They're sticking DNA to gold.
They are. And they use that DNA as a kind of programmable smart glue.
How does that work?
We all know that DNA base pairing is incredibly specific. Adenine, A, only bonds with thymine. T cytosine, C, only bonds with guanine. G.
The Watson crick pairing.
Exactly. So by designing specific DNA sequences and attaching them to the nanoparticles, scientists can program, with atomic precision, which particles will stick together and in what orientation.
Whoa, hold on. So you're not using the electrons in the gold to make the bond anymore. You're using the information encoded in the DNA.
That's it, exactly. You are decoupling the identity of the core particle from its bonding behavior. Normally, gold can only bond in a few specific ways to form a crystal, but with this method, you can make gold nanoparticles assemble into crystal structures that gold would never, ever form in nature.
You're telling the atoms how to build themselves. It's like you're hacking the periodic table.
It is fundamentally rewriting the rules of crystallization. The nanoparticle is the matter, and the DNA is the code that tells that matter where to go and what to connect to.
Unbelievable. Okay, so we have our building blocks, the katoms or the PAEs. But how do we communicate with them? How do you actually program a block of this stuff to turn into a spoon?
That's the input and stimuli challenge. You need a way to talk to the matter. For now, most of the control comes from external fields.
Like magnets.
Magnets, light, electric fields, changes in temperature, even changes in the chemical environment, like the pH level.
This reminds me of those shape memory alloys, the eyeglass frames you can bend all out of shape, and then you run them under hot water, and they snap right back.
That's a perfect analogy for a very, very rudimentary version of this, yes. In that case, the input is heat, and the output is a single predefined shape change.
But programmable matter wants to do more.
Much more. The goal is to move beyond a simple if this, then that response. We want the material to have internal logic. It's not just, I sense heat, so I will bend. It's, I sense heat, and my neighbor to the left is bending this way, and my neighbor to the right is sending me a signal that says, stop, so I will hold my position.
It's distributed computation within the material itself.
That's the holy grail.
This all sounds incredible in theory, but I know science is never that straightforward. There must be massive challenges, which brings us perfectly to the active debate. If this were easy, my phone would probably be reconfiguring itself into a tablet right now. What are the big roadblocks? What are scientists arguing about in the labs?
The roadblocks are monumental, and maybe the biggest one of all is what's known as the co-design problem.
Co-design. What does that mean in this context?
Think about building something traditional, like a car engine. You have a blueprint. You design the pistons, you design the crankshaft, you figure out how they fit together, and then you manufacture them. It's a sequential process. With programmable matter, you have to design everything all at once. You're trying to design the structure of the individual units, the stimulus that will make them change, and the final function or shape it's supposed to achieve simultaneously.
And you're not designing 50 parts. You're designing billions or trillions of them.
Trillions, yes. The design space, which is the total number of possible ways these units could arrange themselves, is, and this is not an exaggeration, larger than the number of atoms in the known universe.
So you can't just guess. You can't use trial and error.
It's completely impossible for a human brain or even a traditional computer to search that space. This leads to this idea of forward design versus inverse design.
Okay, break those down for me.
Forward design is the way we've always done things. I have these bricks. If I stack them in this specific way, what will I get? Oh, it looks like I got a wall.
You start with the parts and see what you end up with.
Right. Inverse design is the opposite. It's saying, I want a wall that can withstand a hurricane and has these specific acoustic properties. Now, computer, you tell me the exact arrangement of trillions of nanoparticles that will achieve that goal most efficiently.
And that's a job for AI.
It has to be. Artificial intelligence, specifically machine learning, is becoming the essential navigator for this impossibly vast design space. Scientists are training models to predict how millions of these units will behave without having to simulate every single particle interaction, which would take forever.
They're trying to treat it like computer code, like zeros and ones.
They are, but the problem is the physical world is not digital. It's analog and it's messy. You have all these other forces at play, van der Waals forces, electrostatics, quantum effects, just random thermal jiggling. It's not a clean binary system.
So the AI has to learn the messy physics, not just abstract rules.
Exactly. It has to learn to navigate what physicists call the energy landscape.
Energy landscape.
Imagine a huge, rugged mountain range with countless valleys. A collection of particles will always try to roll downhill into the deepest valley, which represents the lowest energy state. Usually that's just a useless, disordered clump.
The laziest possible arrangement.
Yes. The job of the AI is to design the particles and the external fields in such a way that it reshapes the entire mountain range so that the deepest, most desirable valley corresponds to the complex, functional shape you actually want.
You're using algorithms to fight entropy.
That's a very elegant way to put it, yes.
Okay, let's talk about power. We touched on this with the Katoms, my chair turning into sand. How do you power 1 trillion microscopic robots? You can't give them all tiny batteries.
You can't. That's the power and energy debate in a nutshell. And it's a huge one. The wiring would be more complex than the object itself. Batteries are too big, too heavy, and don't last long enough.
So what's the solution? Wireless power.
That's one option being explored, but a really fascinating solution is emerging from a recent Caltech study. They call it a kinetic trap.
A kinetic trap?
Yeah.
That sounds like something out of a sci-fi movie.
It's a bit like a molecular mousetrap. Think about a normal spring. When you compress it and latch it, you're storing potential energy. It's just sitting there, stable, but holding that energy in reserve.
It's in a metastable state, ready to snap back.
Exactly. The researchers at Caltech designed complex DNA strands that can be forced into a similar high-energy coiled state. You put energy into the system, usually with heat, and these DNA structures latch into place, trapping that energy.
So the battery is actually the physical tension in the molecule itself.
It is. It's stored mechanical energy at the molecular level. Then when you want the units to move or do work, you introduce a trigger, it could be a catalyst molecule or just a change in temperature, that releases the latch. The stored energy is released, driving the motion.
You recharge the matter with heat.
Yes, and that's the beauty of it. Heat is everywhere. Waste heat from electronics, from engines, solar energy, it opens the door to creating materials that are heat rechargeable, completely untethered from batteries and wires.
That is exceptionally clever. But that brings me to what I think is the most mind-boggling problem of all: scaling and control. The brain problem. How do you choreograph 1 trillion dancers at once?
You don't. You can't. If you had one central brain, one CPU, trying to send instructions to every single unit, the communication bandwidth would be overwhelmed instantly.
It would be like one manager trying to send a unique email to 1 billion employees. The system would just crash.
It would. The latency would make any coordinated movement impossible, so the control has to be decentralized. And the inspiration for this comes directly from biology. It's a concept called artificial morphogenesis.
Morphogenesis, that's how an embryo develops, right?
It is. Think about how a human fetus grows. There isn't a tiny foreman with a blueprint inside the womb telling every cell where it needs to go. The brain doesn't tell a liver cell to be a liver cell.
So how does it know?
It follows local rules. A cell senses its immediate neighbors. It measures the concentration of certain chemical signals or morphogens, and based on that local information, oh, my neighbor is a bone cell, and the concentration of protein X is high, it makes a decision. Then I should become a muscle cell.
And that simple local rule, when followed by billions of cells, creates a complex global structure like a hand.
That is the magic of it. Researchers are trying to encode similar local rules into programmable matter. Each datum only needs to talk to the neighbors it's touching. But the collective result of all those local conversations is the emergence of the complex global shape. It's the idea of ubi materia, ibi geometria, where there is matter, there is geometry.
So you're not building an object, you're growing it.
They're growing it. But even with that elegant solution, we still run into the gritty reality of manufacturing hurdles.
It must be incredibly expensive to make this stuff.
Right now, yes. It's slow and costly to produce either katoms or high-quality DNA-coded nanoparticles, and maybe even more challenging is the problem of defects.
Right. In a computer chip, a single defect in the silicon can ruin the whole thing. Yeah. What happens when a few of your katoms are duds?
Well, this is another area where the biological model is helpful. Your body is full of defects. Cells die or misfire all the time, but the system as a whole is incredibly robust. It can handle errors.
Because it's designed to be fault tolerant. It can self-repair.
Exactly. Our current manufacturing paradigm is based on achieving platonic perfection. But at the nanoscale, that's impossible. There will always be noise, defects, broken units. So the programming, the artificial morphogenesis itself, has to be robust enough to work in a messy, imperfect world.
It needs to be proofed against reality.
That's a good way to put it.
Okay, so the challenges are immense. Co-design, power, control, manufacturing. The labs are making progress. Let's shift to the frontiers. What is actually being built? I was really intrigued by this thing called the chemputer.
Ah, the chemputer. This is a remarkable innovation coming largely from Lee Cronin's research group in Glasgow. It's essentially a universal chemical robot, a robot chemist.
That sounds cool, but what's the big deal? We've had automated lab equipment for years.
We have, but this is different. Think about chemistry today. It's still a bit like cooking. You follow a recipe in a research paper, stir for 20 minutes, add 10 milliliters of this, heat to 80 degrees Celsius.
Okay.
But that recipe is incredibly subjective. How fast is stir? What's the shape of your flask? What's the humidity in your lab today versus my lab tomorrow? This lack of precision kills reproducibility, which is a massive problem in science.
My results might be different from yours even if we follow the same recipe.
They often are. The chemputer aims to solve this by digitizing chemistry. They developed a universal programming language for chemical synthesis called XDL.
XDL, chemical description language.
Exactly. It breaks down every physical action, add liquid, heat vessel, stir at RPM into a standardized hardware-independent code. The robot executes the code.
So you're not sharing the recipe anymore, you're sharing the source code.
Precisely. It means you could, in effect, email a molecule. I can run the code on my chemputer in London. You can run the same code on yours in Tokyo, and we get the exact same result. It's universal, and it's reproducible.
And they proved this by making something, right? 8,2-hexane?
8,2-hexane, yes. It's a type of molecular machine.
What is that?
Imagine a tiny acyl molecule with bulky stopper groups on each end, and threaded onto that acyl, like a bead on a string, is a ring-shaped molecule. The ring can shuttle back and forth along the acyl, but it can't fall off.
So it's a mechanical bond, not a chemical one, like a tiny piston or switch.
It is. It's one of the fundamental components for building more complex molecular machinery. And the chemputer synthesized one of these autonomously.
From scratch?
From scratch. It took about 60 hours and involved over 800 distinct robotic steps. Threading the ring onto the acyl, capping the ends, purifying the product, all without a human hand touching it.
That's incredible.
And the implication is huge. If we want programmable matter, we need to be able to mass produce its components, the molecular motors, switches, and gears. The chemputer is like the first universal factory for those components.
It's a game changer. What about something called Programmable Active Matter, PM?
PM is matter that continuously consumes energy from its environment to stay out of equilibrium.
Out of equilibrium. That sounds like a physicist's way of saying alive.
It's getting very close. A rock is in equilibrium with its surroundings. It's the same temperature. It's not moving. A person is out of equilibrium. We consume food to maintain our body temperature and to move. Active matter does the same.
And this leads to liquid robots.
It does. There's work from UC Santa Barbara and TU Dresden on robots made of materials that can toggle between a solid, rigid state and a liquid state.
Now, I'm trying very hard not to reference a certain sci-fi movie villain from the early 90s.
Yeah. We're all thinking it. But beyond the cinematic cool factor, think of the practical applications. A search and rescue robot that can flow like a puddle under a collapsed doorway and then reform on the other side and become rigid enough to lift debris.
That would be revolutionary. And this active matter can also think. I read about DNA computing.
This is where the lines get really blurry. Researchers have successfully created what are essentially neural networks in a test tube using DNA. They've shown that these DNA circuits can recognize handwritten numbers.
Wait, you're telling me a beaker of liquid can read?
It's not reading with eyes. They expose the DNA mixture to different molecular concentrations that represent the pixels of an image, the digits 1 through 9. The DNA strands then interact, competing with each other in a complex chemical reaction.
And the calculation is just the molecules randomly bumping into each other.
It's computation driven by Brownian motion, yes. A winner-take-all process where the final stable chemical state corresponds to the correct answer. They identify the digits with high accuracy.
So you can build materials that can sense and process complex information without a single silicon chip.
A material that can think. That's the implication.
This seems to connect directly to the idea of 4D printing,
It does. We're all familiar with 3D printing now, which is creating a static object layer by layer. 4D printing adds the fourth dimension, time.
meaning the object changes after it's been printed.
Correct. It's printed in one state, and then it transforms into another based on a stimulus from the environment, a change in humidity, temperature, or exposure to light.
What's an example?
A fantastic one is a medical stent for a blocked artery. You can 4D print it in a compressed, compact form that's easy for a surgeon to insert. Then, once it's in the body, the patient's body heat acts as the trigger.
And it expands to the perfect size and shape to open the artery.
Exactly. And you could even design it to become more or less rigid over time, adapting to the patient's healing process or responding to their blood pressure. It's hardware that behaves like software.
And rounding out the frontiers, we have metamaterials.
Metamaterials are fascinating. They are artificial structures whose properties are defined by their geometry, not their composition. You can have mechanical metamaterials where the way a tiny lattice structure deforms can be used to store a binary bit of information, a 0 or a 1.
So the material structure is the computer memory.
Yes, the data is stored in the physical shape of the material itself. And then you have electromagnetic metamaterials, which are surfaces engineered with tiny patterns that can manipulate radio waves or light in ways that are impossible for natural materials.
This is the technology behind invisibility cloaks, isn't it?
This is the basis for it, yes. By precisely controlling the refractive index across a surface, you can bend light waves around an object, making it appear as if it isn't there.
We've literally gone from static bricks to invisibility cloaks in one conversation. The pace of this is staggering.
It's an incredibly exciting time in material science.
It certainly is. Okay, so we have the science, we have the challenges, we have the cutting-edge prototypes. Let's talk about the big picture. What does this all mean for us? What are the implications?
I think the most profound and perhaps most immediate implication is for sustainability in the circular economy.
How does this super high-tech field help the environment? It sounds like it would create more problems than it solves.
It seems that way, but think about our current economic model. It's take, make, dispose. We extract raw materials, manufacture a phone, you use it for 2 years, and then you throw it in a drawer or a landfill. The material is locked into that form forever.
Right.
Now imagine an internet of materials. Your phone is made of programmable matter. When a new model comes out, you don't buy a new device. You download a software patch, and the matter reconfigures itself into the new shape with the new button layout.
So I'm not throwing anything away. I'm just updating the physical form.
You're updating it.
Yeah.
And when the product is truly at the end of its useful life, you can apply what some call the R6 and R8 principles of recycling.
R6 and R8. I'm not familiar with those.
R6 is the principle of disassembling materials from one product to be used as raw feedstock for a completely different one. Because the building blocks, the atoms or PAEs, are standardized, you can literally melt down your old smart toaster and reform the matter into a new pair of shoes.
It's the ultimate form of recycling. The matter is universal.
It is. And R8 refers to automated sorting. One of the biggest bottlenecks in recycling today is separating different types of plastics and metals. It's difficult and expensive. But if the material itself is smart, it can tell the recycling facility what it is. It makes the whole process vastly more efficient.
That's a fundamental shift. And what about self-healing?
That's another huge part of the sustainability picture. Imagine a concrete bridge that can automatically detect and fill its own microcracks, or an airplane wing that can repair fatigue damage in flight.
You'd extend the lifespan of our infrastructure dramatically.
Dramatically, which means consuming far fewer resources to replace things. It improves safety and saves an enormous amount of money and material.
Speaking of money, what's the expected economic impact of all this?
The projections are, as you might expect, pretty aggressive. The market is currently small, but it's projected to grow from around $1.5 billion in 2025 to over $12 billion by 2035.
That's almost tenfold growth in a decade. Which industries are driving that?
The biggest share right now is defense and military. The applications are obvious: adaptive camouflage, self-assembling drones, instant shelters. But the fastest growing sector, by far, is healthcare.
The healthcare revolution. Tell me more about that.
We talked about the smart stent, but expand that to things like bone implants. Imagine an implant for a fractured leg that starts out incredibly rigid, but as the bone heals and gets stronger, the implant gradually becomes more flexible, transferring the load back to the bone to ensure it heals properly.
It adapts to the patient's own recovery process.
Day by day. Or think about programmable mRNA therapeutics drugs that can be delivered to the entire body in an inactive state and then activated only at a specific tumor site by an external signal, like ultrasound.
So you avoid all the side effects of chemotherapy.
You could. Or DNA robots that can swim through your bloodstream, identify specific pathogens, and deliver a payload to destroy them. It's precision medicine at the molecular level.
It really is the fantastic voyage scenario coming to life. And what about beyond Earth? Space exploration.
Space is one of the most compelling near-term applications, actually.
Why there specifically?
Because of something called the tyranny of the rocket fairing. The nose cone of a rocket has a fixed and fairly small diameter. Anything you want to put in space has to fit inside it.
Right. It's a huge limitation on the size of things like satellites or space telescopes.
It is. You have to build these complex origami-like structures that unfold in space, which is risky. But with programmable matter, you could launch a hyper-dense, compact brick of the raw material.
It's just a solid block of cadmiums.
Exactly. It takes up very little volume. Once it's in orbit, you send a signal, and that brick autonomously unfolds and assembles itself into a massive radio antenna, or a solar sail, or a section of a space station.
We're launching potential, not a finished object.
You're launching potential. It completely bypasses one of the fundamental constraints of getting things into space.
It's just staggering to think about. We've gone from the theoretical concept of information as physical all the way to self-assembling space stations. But I know you always like to leave us with one final provocative thought to chew on.
I do, and it circles all the way back to that line between life and non-life. It's this idea of soft matter brains.
Soft matter brains.
We've talked about materials that can process information, like the DNA computers. We've talked about active matter that consumes energy to move and stay out of equilibrium.
Okay.
The human brain is a perfect example of this. It's made of soft matter, it's wet, it's squishy, it consumes energy about 20 watts to process information incredibly efficiently.
I think I see where this is going.
If we become masters at designing programmable active matter that can sense its environment, process complex information, and consume energy, are we not, in effect, moving toward building materials that are, for all intents and purposes, alive? The line that we've always drawn between biology and geology, between a living thing and an inanimate object, is starting to become incredibly blurry. We're not just building smarter tools. We might be on the verge of building a new kind of synthetic life, a geology that can think.
A thinking rock. That is a beautiful and, frankly, slightly terrifying thought to end on. A new form of life born not from biology, but from geometry and code.
It's a future we need to start thinking about.
Indeed. Well, on that existential note, I think that's a perfect place to wrap up. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.